let's try to finish up this chapter. All right, so as we were talking about in the last video, we find that the light curves agree to the experimental, the light curve that we see when we look out into the universe, when we're looking at supernova explosion, and the one that we have theoretically, they have a very great agreement. And this last idea, this is what I was ending in the last video with, is that there is this gigantic idea about recycling. Is essentially the universe does this all on its own. Okay, so let's go through this idea. When the universe was created 13.8 billion years ago, and we'll get to this towards the end of the semester, there is hydrogen and helium available to form stars. Okay, when the stars die, they create heavier elements. That's what part of this chapter was all about. What elements can be created during the death of stars, like either type 1 or type 1 or type 2 supernova. And of course, the earlier chapters dealt with just the death of an ordinary low mass star, and that of course is creating elements, and that those elements are spread out into the universe by way of the planetary nebula phenomenon, right? That our star will ultimately undergo in about 5 billion years. But anyhow, so the low mass stars, again, the majority of stars are the low mass stars. So there's a lot of material out there, especially carbon, nitrogen, and oxygen from these low mass stars. And then we find that the star is just slightly more massive than the sun. Up to about 8 times the mass of the sun, can undergo dramatic explosions, which are of course the type 1 supernova, and then even more massive than 8 times the mass of the sun. They can create type 2 supernova, and the type 2 supernova will produce some of the the heaviest elements that we find in the universe. And to a lesser extent, the type 1 supernova do this as well. Anyhow, what's going on when these stars die? The material that they created, the material that they transformed, it would be a better description of it. Through nuclear processes, the heavier elements become, the lighter elements become heavier elements, all the way up to uranium, element 92. And that material ends up, especially due to explosions, but and also to planetary nebula phenomena, the material ends up out in the galaxy again, right? In between the stars, in what's called the interstellar medium. And so, of course, the interstellar medium is where new stars can be born. Not always, but they can be born. They can be formed from this material, these giant clouds of gas and dust. And what we're seeing, of course, is the evolution of stars puts heavier and heavier material out there in the interstellar medium of our type of galaxy, of the spiral galaxies. We'll get into different types of galaxies a little bit later. But if you just think about the Milky Way for a minute, for a little while, the spiral galaxies within the disk, the spiral galaxies like the Milky Way within the disk of the galaxy, there is heavier and heavier elements that are being produced as stars die and spread that material out. New stars are born. Those stars eventually die, and then our star, we think, is a third generation star. So some supermassive star died long ago in the early parts of the Milky Way galaxy, perhaps 12 billion years ago, and then heavier elements got out into the interstellar medium, created another star, and other stars. It's not just like it doesn't go from one to one, right? I mean, many stars contributed to the heavier elements that we find in the interstellar medium. And then when our star formed about 4.5 billion years ago, there was plenty of material that was all the way up to uranium out there in the interstellar medium from dead stars, right? That's where it comes from. It comes from dead stars. And so our star forms in 5 billion years from now. That material, some of it anyway, will go out into the interstellar medium, and so there'll be heavier elements. And so as time goes on, you're going to get heavier and heavier elements out there in the universe, and stars will be created with more and more heavy metals. So right now, the stars that are created are, including our sun, is called a population 1 star. The stars that were created, in the last 10 billion years, up to about 10 billion years ago, those were, but it's not exactly an age thing, although it is related to the age. But it also depends on where the stars were created, because different parts of the galaxy have undergone more evolution than other parts of the galaxy. Anyhow, the older stars were created from material in the interstellar medium that doesn't have as much metal, and so those are called population 2 stars. And in fact, we think that there were originally population 3 stars that formed from just pure hydrogen and helium. Those stars don't exist anymore, right? We don't find them out there in the universe. Although we do find some stars that are really close to what we would consider population 3 stars, which would be absolutely no hydrogen and helium. But there's always these small trace amounts, even in very, very old stars that we find. All right, so because material gets spread around, there's no stars that are out there just completely in isolation. The material gets spread around, and that's what this is showing. Is as time goes on, you get heavier and heavier elements that are spread throughout the galaxy, and new stars get formed, and you get heavier and heavier elements. All right, let's finish this chapter. So we started with talking about just novas. These are just stars about the size of the sun or smaller, which turn into white dwarfs. But then, of course, there is a companion star that is close enough so that material will pile up on that star and explode, and it's really a helium explosion that takes place. Sometimes you have stars that are, of course, greater than 8 times the mass of the sun, and fusion can occur all the way up to iron, which is very, very stable, and does not fuse any further. Basically, what happens is the star doesn't gain any energy by fusing hydrogen. By fusing iron. As we saw, there can be what's called neutron capture, which can create elements all the way up to bismuth. So you're getting most of the periodic table created, and then of course when the star does try, if the star is massive enough and it does try to fuse iron, what happens is the core will collapse in on itself, and it's basically a very rapid implosion, and then that implosion turns into an explosion where material flies out away from the star, and that's what we see as the supernova remnants. And so, there's two types that we've identified, two general types. Type 1 is a relatively low mass star where there's a white dwarf and material falls onto the white dwarf. If enough material that exceeds 1.4 times the mass of the sun falls onto this, so the total mass of the star plus new material that's falling onto it exceeds 1.4 times the mass of the sun, which is also known as the Chandra-Zahar mass. Then the star cannot hold itself up due to electron degeneracy pressure, which is pushing back on, trying to prevent the star from collapsing in on itself. The thing is, beyond electron degeneracy pressure, what happens is neutrons and electrons will merge in the nucleus and form neutrons. When that happens, the core of the star is basically a neutron, and we're going to actually talk about that in the next chapter. What are called neutron stars. Some neutron stars can actually form what we call black holes, which we'll talk about in great detail in the next chapter. Anyhow, those stars explode, and these carbon detonation supernova can explode, or do explode, and you can form heavier and heavier elements, and that material goes out into the universe. Type 2 supernova is really what we expect there to be remaining material after. Like, it seems that the type 1 explosions, everything explodes. There's not a lot left over. The type 2 explosions, there can be stuff left over, and what happens during a type 2 is you're creating elements all the way beyond bismuth, all the way up to and including uranium. Right, during and that's very little compared to the amount of iron and oxygen and nitrogen and carbon that's produced out there in the universe. But there's still some of it, right? There's some uranium, things like that. All right, so that is the end of the chapter, and yeah, we'll stop it there. We're going to move on to neutron stars and black holes, and the theory of general relativity, Einstein's theory of gravitation.